Hello everyone, my name is Blaha Gregory Correia dos Santos Goussain, and I am pleased to welcome you to this presentation. Today, I will present our research titled Rule-Based Expert System for Risk Analysis and Mitigation in Construction Projects. This work was developed in collaboration with Sinai, Ceifet MG, and UNESP, and was presented at ICDTDE2025. Over the next 12 minutes, I will explain the motivation behind this project, the challenges faced in construction risk assessment, the architecture of the proposed expert system, and the main findings of our validation study. Construction projects inherently involve complexity and uncertainty. They are exposed to environmental conditions, contractual variables, human factors, and logistical challenges. These uncertainties often lead to delays, cost overruns, and safety incidents. Traditional risk assessment methods rely heavily on subjective expert judgment, which may introduce inconsistencies and hinder reproducibility. In many cases, evaluations are performed manually without systematic reasoning or automation. Because of this, there is a growing need for transparent, consistent, and interpretable tools to support decision-making in construction management. Our motivation was to explore how rule-based expert systems can formalize expert reasoning and help mitigate risks more effectively. The key problem we address is the lack of accessible, explainable, and automated tools for risk assessment in construction projects. Current approaches often suffer from important limitations. Many machine learning models behave as black boxes, offering little interpretability. Existing software tends to be complex and unfriendly for engineers who are not programmers. Manual risk priority number calculations are time-consuming and prone to inconsistencies. Tools developed for one project often lack scalability and reproducibility for others. Therefore, the main challenge becomes, how can we create an interpretable, low-cost, rule-based system that automates risk analysis while remaining easy to use? The objective of this research was to develop and validate a rule-based expert system capable of performing automated risk assessment in construction projects. More specifically, the system automates RPN computation using a CLIPS inference engine, provides a practical and accessible Python/TKINTERG UI, ensures explainable and traceable reasoning, supports organizations in identifying, classifying, and mitigating risks efficiently. Our goal was to bridge the gap between AI theory and practical engineering applications, offering a reliable tool for real-world construction contexts. Here we present the architecture of the proposed system, which consists of 3 fully integrated components. The knowledge base contains 20 critical construction risk factors, represented in structured rule templates following FMEA logic. The inference engine implemented in CLIPS uses forward chaining logic to evaluate conditions, compute RPN values, and classify risks into low, moderate, or high levels in real time. Finally, the user interface, built in Python with tkinter, allows engineers to input risk information through buttons and drop-down menus, making the system accessible even to users without coding experience. This architecture enables a seamless workflow from data input to automated reasoning and output visualization. The knowledge base follows the standard FMEA framework using 3 parameters: severity, occurrence, probability, detectability. The risk priority number is computed as RPN equals severity times probability times detectability. Rules define risk categories. Low risk when RPN is less than 50. Moderate risk when 50 is less than or equal to RPN 125. High risk when RPN greater than or equal to 125. All rules and variables were defined by experienced construction professionals, ensuring that the reasoning embedded in the system reflects expert judgment in a structured and consistent way. To illustrate how the system works, one rule handles environmental impacts. When the user selects yes for a specific environmental risk, the rule assigns an appropriate severity level and detectability value. The engine then combines this rule output with the probability selected by the user to compute the final RPN. This approach allows the system to present not only the result, but also the logical explanation behind it, ensuring transparency and interpretability. The system was validated in 2 stages. First, we created 50 simulated scenarios representing environmental, contractual, and scheduling risks. These scenarios allowed us to test system consistency across diverse situations. Second, we conducted an expert assessment involving 5 construction professionals. Each expert evaluated 10 scenarios manually, and their results were compared to the system's automated output. Performance was evaluated using standard metrics: accuracy, precision, recall, F1 score, and usability through the system usability scale. The expert system demonstrated strong performance. Accuracy reached 92%, indicating high agreement with expert evaluations. Precision was 0.89, meaning the system rarely classified risks incorrectly. Recall reached 0.98, showing excellent ability to identify high-risk scenarios. The F1 score of 0.93 reflects balanced precision and recall. Average inference time was just 1.2 seconds, meaning the system can be used in real-time decision-making. The SU's usability score was 82 out of 100, which is considered excellent for interactive systems. We also conducted a paired t-test to compare manual RPN values with system-generated RPN results. The test produced a statistically significant result: T49 equals 2.14, P equals 0.038, with a moderate effect size of D equals 0.62. These results show that the system's outputs are statistically consistent with expert judgments. Additionally, the integration of the tkinter GUI with the CLIPS engine reduced evaluation time by nearly 70%, demonstrating that the system improves both accuracy and efficiency. The risk distribution analysis revealed that high-risk scenarios were primarily associated with environmental impacts, contractual ambiguities. Moderate risks occurred frequently in situations involving critical path scheduling dependencies. Across all evaluated cases, the average RPN was approximately 95.8, placing most scenarios in the moderate risk category. Compared to other knowledge-based systems, our approach demonstrated higher transparency, faster inference, and improved reliability. The user interface was designed to simplify interaction for construction engineers. Radio buttons and drop-down menus reduce input effort, while immediate visualization of RPN values enhances user confidence. This aligns with current principles in explainable AI, where clarity and traceability are essential for trust in automated systems. By reducing cognitive load, the system enables project managers to focus on decision-making rather than manual calculations. Compared to other approaches, fuzzy FMEA offers flexibility but suffers from higher complexity and lower transparency. Machine learning models often work as opaque black boxes. Case-based reasoning systems achieve around 88% effectiveness, lower than our 92%. Our system delivers greater interpretability, faster inference, open source, and low-cost implementation. This makes it especially valuable for organizations with limited digital resources. The expert system supports real-time monitoring, enhances decision-making, and improves the standardization of risk assessment processes. It can be expanded to interact with BIM platforms or enterprise-level management tools. In addition, it offers training benefits by teaching professionals how structured rule-based reasoning works, fostering better understanding of risk management principles. Naturally, the system has limitations. Because it relies on predefined rules, it may not adapt to emerging risks without manual updates. Qualitative inputs can introduce subjectivity, and the validation was performed using simulated scenarios rather than live construction projects. These limitations highlight opportunities for continued development. Future work may explore hybrid models that combine rules, fuzzy logic, and machine learning. Cloud-based and multilingual interfaces can increase accessibility. Dynamic rule updates based on expert feedback would enhance adaptability. Real-world validation in active construction sites as well as integration with IoT sensors for autonomous risk monitoring represent important next steps. In conclusion, we developed an interpretable, rule-based expert system that automates risk assessment for construction projects. It demonstrated strong accuracy, high usability, and significant time reduction compared to manual evaluation. This system helps bridge the gap between artificial intelligence research and practical engineering applications. It represents a scalable, low-cost tool that can contribute to safer and more efficient construction management. Thank you very much for your attention. I will be happy to answer any questions or discuss future collaborations. If you wish to contact me, my email address is blaha.goussain@unesp.br.